Welcome again to Horizon Summer School Blueprints of the Universe. Today, myself, Shri Kiran, Vatsal, and Kirtana, students from IIT Madras, will be covering the topic antenna theory. Antennas are a key part of almost every modern communication system, from mobile phones and Wi Fi to satellites and radio astronomy. They serve as the link between electrical signals and electromagnetic waves, making wireless communication possible. In this session, we'll look at what antennas are, how they work, uh, the considerations that go into designing them, and why understanding them is essential for anyone working with modern technology. So, what is an antenna? It is a means of receiving or transmitting electromagnetic waves. It converts electromagnetic waves into alternating current to receive a signal, after which the signal is amplified. For transmission, an alternating current is supplied to the antenna, which radiates energy in the form of EM waves. So you can notice that even a light bulb is a sort of antenna, since it takes in alternating current and radiates EM waves in the visible range. And now, why should anyone study antenna theory? Studying antenna theory helps us understand how wireless communication systems work at a fundamental level. It provides us the tools to design and analyze antennas for different applications, ensuring efficient transmission and reception of signals. Uh, Wireless communication is the backbone of the modern world, and whether it's for mobile networks, satellite links, or radar systems, a solid understanding of antenna theory is essential for developing reliable and effective communication technologies. Now we'll be going over the history of antennas. Maxwell's theory of electromagnetism predicted that coupled electric and magnetic fields could travel through space. For a while, there was no experimental demonstration which proved the existence of electromagnetic waves. In 1886, Heinrich Hertz demonstrated the first experimental evidence of these EM waves. He produced a spark through a gap in a metal rod, which induced a spark in a loop of wire nearby. This was the first antenna. Marconi worked on making this newly discovered technology useful for communication. Uh, at the age of 20, Marconi began to conduct experiments in radio waves, building much of his own equipment in the attic of his home. One night, Marconi demonstrated a radio transmitter and receiver to his mother, a setup that made a bell ring on the other side of the room by pushing a telegraphic button on a bench. A breakthrough came in the summer of 1895 when Marconi found that a much greater range could be achieved after he raised the height of his antenna, and borrowing a technique used in wire telegraphy, he grounded his transmitter and receiver. In 1901, he sent wireless telegraph signals across the Atlantic Ocean, after which his system was used regularly for communications between ships and docks. In the image on the right, you can see an example of a radio telegraph. And you'll be able to notice over here that it's actually Morse code. So you can see here that a B is a long beep and then followed by three short beeps. And an E is a short beep and so on. So that's how they would communicate. And this is the station at Cornwall, which he used to sent the first wireless telegraph signal across the Atlantic Ocean. After this, ships and docks began to use his technology for communications. So, a fun fact: the Eiffel Tower was originally meant to be demolished 20 years after its construction in 1889. The artists of the artists of France and Paris were protested against its construction since they thought it would be a hideous obstruction to the city's skyline. The letters they sent to the government were also quite poetic, and that's how you could tell that the letters were sent by artists. However, the development of radio antennas saved it, as it then found use as a place to mount antennas on. Prior to the World War, Prior to World War II, most antennas were of the wire type. So you'd have dipoles and loops and those kind of antennas. During the World War, aperture antennas were developed. So these are like horns and satellite dishes, sort of. And these developments came through because of the application in radar systems. On the right, you can see an ex-World War II antenna, which was later repurposed to detect solar radio emissions. And now I'll be handing over to Kirtana, who will discuss the history of radio astronomy.
Hello. Um, I'll be going over the history of radio astronomy, as Srikaran said. So, the origin of radio astronomy happened serendipitously in 1933 when Carl Jansky, an engineer working in Bell Laboratories, constructed an antenna to identify sources of static interference that disrupted radio communications across the Atlantic. An interesting fact about his antenna, which is shown in the picture, is that since it could rotate, it was often referred to as Jansky's merry-go-round. The antenna was designed to capture the 20.5 megahertz frequency, and Jansky categorized the static he observed into three types: static originating from nearby thunderstorms, from distant thunderstorms, and a third type, which he did not know the cause of at the time. He then observed the intensity. He then observed that the intensity of the static peaked every 23 hours and 56 minutes, which indicated, firstly, that the signal was not random noise. Uh, the fact that it repeated every 23 hours and 56 minutes and not every 24 hours indicated that the sun was not the source, and that um, it was extraterrestrial in nature. This is because 23 hours and 56 minutes is the length of a sidereal day, which is determined by the Earth's rotation with respect to distant stars. And on further observation, he found that the emission was coming from the direction of the constellation Sagittarius, which lies towards the center of the Milky Way. Despite um, despite this, Jansky's findings did not initially garner attention from the scientific community. And in addition to this, Bell Labs had rejected his proposal for building a larger 30-meter dish to study these emissions. His findings did, however, get the attention of someone who is often considered to be the world's first radio astronomer. In 1937, Gro Trevor, an American radio engineer and amateur radio operator, constructed the world's first radio telescope with a 9-meter parabolic dish in Wheaton, Illinois. Reber not only confirmed Jansky's findings, he was also able to observe a wider range of frequencies than Jansky was, and he produced the first radio maps of the galaxy at various wavelengths and identified several important discrete radio sources. He also provided early evidence that galactic radio emission was non thermal in origin. Let's now take a look at some seminal discoveries in radio astronomy. Firstly, we have the 21 centimeter hydrogen line. Um, in 1951, American physicists Harold Irwin and A.M. Purcell detected the 21 centimeter radiation emitted by cold clouds of neutral interstellar hydrogen atoms. And this was a significant breakthrough since the 21 centimeter line can penetrate interstellar dust and gas without significant absorption, unlike visible light. This allowed scientists to precisely map the spiral arms of the Milky Way and determine its rotation curve. It provided an understanding of galactic structure and dynamics that may not have been obtained through visible light. Followed by this was the discovery of the cosmic microwave background. In 1964, Arno Penzias and Robert Wilson were experimenting with the horn antenna, which was initially designed to detect faint radio waves that bounced off echo balloon satellites. While doing so, they encountered a persistent noise, which was present despite performing exhaustive checks on the equipment. And this even included the removal of pigeons that were nesting on the antenna. Um, they they estimated its temperature. They estimated the temperature of the signal to be around 3.5 Kelvin. And although they did not know it at the time, this matched the predictions of Robert Dicke and James Peebles, who claimed that microwaves should be detectable throughout the universe as a result of the Big Bang. This would later come to be known as the cosmic microwave background, and its detection served as evidence for the Big Bang theory, providing insights into the origins of the universe. Penzias and Wilson were awarded the Nobel Prize in 1978 for their measurement of CMB. Another significant development in radio astronomy is the discovery of quasars. And quasars were named as an abbreviation of quasi-stellar radio source, and they are powerful radio emitters that, when observed at visible wavelengths, resembled faint star-like points of light. Early quasars, such as 3C48 and 3C273, were first noted in all-sky radio surveys for their intense radio emission and either a lack of a clear visible counterpart or an extremely small angular size. In 1960, in 1962, Cyril Hazard and John Bolton, using the Parkes Radio Telescope, observed 3C273, and these observations were used by Martin Schmidt to identify its visible counterpart and then obtain its spectrum using the Hale telescope. Schmidt found that its spectrum had a significant redshift of 0.16. This high redshift, um, through uh, Hubble's discoveries, uh, this high redshift determined this high redshift implied that quasars were not nearby stars in our galaxy, but instead were extraordinarily distant and luminous objects, much brighter than most galaxies. Now, quasars are understood to be the active galactic nuclei of distant galaxies, powered by matter spiraling into supermassive black holes at their centers. Observations have shown that quasar activity was far more prevalent around 10 billion years ago. So, quasars could provide insights into the early evolution of galaxies. The discovery of pulsars was uh, the next significant event in the history of radio astronomy. The discovery of pulsars began in 1965 at the Mallard Radio Astronomy Observatory in Cambridge during the construction of a new telescope designed for quasar detection. While performing data analysis for the same, Jocelyn Bell, who was a graduate student at that time, found signals that were initially dismissed as noise or interference. In 1967, Bell and her supervisor, Anthony Hewish, concluded that the signal was a series of periodic pulses with a time period of exactly 1.337 seconds. The signal's extraterrestrial source was confirmed by the fact that they appeared once every 23 hours and 56 minutes, which is the length of the sidereal day. Pulsars are now understood to be highly magnetized, rapidly rotating neutron stars that emit focused beams of electromagnetic radiation from their magnetic poles. And the pulses that are observed occur when the radiation sweeps across the Earth. The discovery of pulsars was seminal, and although the 1974 Nobel Prize was awarded for this discovery, it was awarded to Anthony Hewish and Martin Ryle, but not Jocelyn Bell, despite her observation and analysis being indispensable to the discovery. The discovery of pulsars revealed the existence of neutron stars and enhanced our knowledge of stellar behaviors, opening up new avenues for understanding the behavior of matter in the extreme physical conditions present in a neutron star. And one interesting pulsar that I want to mention is the Hulse-Taylor pulsar, which is the first pulsar that was discovered to be in a binary system. It was discovered in 1974 and is named after the scientists who discovered it, and it provided the first indirect evidence of gravitational waves. Now that we've looked at a few significant discoveries in radio astronomy, let's take a look at some of the most prominent radio telescopes in the world. The picture on the left is of the Arecibo Observatory in Puerto Rico, which was initially built for radar studies of the Earth's ionosphere, although it ended up being used extensively for radio astronomy. Its most recognizable feature was a 305-meter fixed spherical reflector, and it was steered not by moving the dish, but instead by moving a suspension feed platform within around 20 degrees of the zenith. Arecibo was, in fact, the observatory that studied the Hulse-Taylor pulsar and provided indirect evidence of gravitational waves. It was also the observatory that discovered the first extrasolar planet, which was a pulsar planet. Sadly, the central instrument platform of the telescope collapsed in December 2020, and the observatory is no longer in use as a result. The other picture on the slide is of the 500-meter aperture spherical telescope located in Guizhou, China. It's the world's largest single-dish radio telescope, and its structure includes an active main reflector, which corrects spherical aberration on the ground. It operates across a wide frequency range, from 70 MHz to 3 GHz. Scientists aim to use it to observe pulsars extensively, as well as to conduct large-scale neutral hydrogen surveys using the 21 centimeter line. The telescope is also participating in the search for extraterrestrial intelligence. So the previous slide um, had a glimpse of some prominent single dish telescopes. Uh, and these are some, and the ones on this slide are some very well known radio telescope arrays. The one on the left is the Very Large Array. It's known as the Carl G. Jansky Very Large Array, and it's located in New Mexico, USA. It consists of 27 parabolic dishes, each of which can be moved independently. This allows astronomers to adjust its resolution and sensitivity depending on the object that they are observing. The VLA is the most widely used radio telescope. and has been used to observe astrophysical phenomena, including black holes, protoplanetary disks, and including black holes and protoplanetary disks around young stars. The next image on the slide is of the Atacama Large Millimeter Array, which is located, as the name suggests, in the Atacama Desert in Chile. It consists of 66 dish antennas that are designed to observe wavelengths of the order of millimeters. It has detected some of the most distant oxygen molecules known, which provides evidence for unexpected early star formation just 250 million years after the Big Bang. It has also observed star forming galaxies and protoplanetary disks. One of its missions is to detect emissions from organic molecules. The observatory also played a significant role in the Event Horizon Telescope collaboration, which captured the first image of a black hole. The image on the right is the low frequency array, and this consists of 51 antenna stations spread across Europe, and its steering is done through electronic beamforming rather than physically moving its parts. This telescope is designed to observe some of the radio frequencies observable from Earth from 10 to 240 megahertz. And these are some of the lowest radio frequencies that can be observed from the Earth. One of its main objectives is to observe the primordial era of the universe before the formation of the first stars and galaxies, specifically by detecting the 21 centimeter line. It also aims to study solar activity and its effects on Earth's space environment. Having looked at the wide range of areas in which antennas are used, let's take a look at their working. The diagram on the right shows an AC source connected to a two conductor transmission line and an antenna. The electric fields and the corresponding charges on the antenna are shown in the figure. As a result of the AC oscillations, guided electromagnetic waves propagate through the antenna as shown in the first diagram. The second diagram shows the propagation of free waves through space. This occurs after the detachment of the wave from the antenna. This can be thought of with an analogy with water waves. When there is a disturbance in a water body, it generates waves through water, which propagate even after the disturbance is removed. Another thing to note in the second diagram is the connections between the open ends of the electric field lines, which is indicated with a dashed line. When the electromagnetic waves are within the transmission line and the antenna, they are associated with charges in the conductors. However, when the waves are radiated, they form closed loops without charges to sustain them. Now, Srikaran will speak on the radiation pattern of antennas. Over to Srikaran.
Thank you, Kirtana. So this is a very basic parameter of antennas. The radiation intensity in a given direction is the power radiated from an antenna per unit solid angle. So this is like how much power is being transmitted from an antenna in a particular direction. And the radiation pattern is a plot where each is a plot of the radiation intensity in all the different directions. You can think of it as a plot where each point represents a direction and the distance of the plot from the origin is like a measure of how strong the signal is in that direction. Uh, Also, if I add up the total power over the entire overall directions, I should get the total power radiated. On the right, you can see an isotropic antenna, or at least the radiation pattern of an isotropic antenna. An isotropic antenna is one which radiates uniformly in all directions. So it's an antenna that radiates the same power in all directions. And such antennas actually don't exist in real life. They are just a theoretical tool. Uh, and its radiation pattern is very clearly just a sphere. And now I will cover the most basic type of antennas, the dipole antennas. So on the right, you can see a half wave dipole antenna. So half wave basically just means that the length of this total length of this antenna is one wavelength, and you get this antenna by so in this image you just bend the ends a little more until they reach 90 degrees, and then you get this half wave dipole antenna. So what's special about a half wave dipole antenna is that it is resonant. What do I mean by resonant? So we are using an AC current source. That means that the current has a phase associated with it. So let's say that the current over here has some phase. This length of the antenna is lambda by 2. So we'll go up, travel a lambda by 2. Sorry, it's actually lambda by 4 since the total length is half a wavelength. So half of the antenna itself is lambda by 4. So this length is lambda by 4. So once the current travels from here to here, its phase has changed by lambda by 4 into 2 pi, which is pi by 2. And there is nowhere else for the current to go after this. So it just gets reflected back. And because of that reflection, it suffers another phase change of 180 degrees or pi radians. And then when it comes back again, it has again traveled a lambda by 4 distance, which is equivalent to a pi by 2 uh, phase. So pi by 2 plus pi by 2, that gives me a 2 pi phase. And the phase difference between uh, the current that is entering over here and the current that has been reflected back is 0. So what happens now is since the current is in the same phase, they add constructively, and you get standing waves throughout this antenna, similar to the kind of standing waves you'd see on a string. You'll have fixed nodes and antinodes, and also the current at the antinodes is maximum at resonance. Similar to how in a vibrating string, the displacement is maximum only when you have standing waves. So the current at the antinodes is maximum, and also the current distribution itself is such that the current distribution in the two halves of the dipole is such that the electromagnetic waves combine constructively. And the radiation pattern of the dipole antenna is an omnidirectional pattern. So omnidirectional here means that you have an axis about which if I rotate the pattern through any angle, the pattern will look the same. So now we come to short dipole antennas. These dipole antennas, so they don't have as much, they don't have enough length to create standing waves. So you can't have a 0 phase difference or a 2 pi phase difference or any multiple of 2 pi. So you can't get resonance in short dipole antennas. Typically, the length is much less than lambda by 10, and You use these only when space is limited, since they are inefficient, since they can't reach resonance. Now I hand it over back to Kirtana.
Thank you, Srikiran. Um, Let us take a look now at modeling antennas as RLC circuits. So, so RLC circuits have three main elements: inductance, capacitance, and resistance. The inductance of an antenna um, arises from the magnetic fields generated by the current flowing through the antenna's conductive elements. We all know that all conductors possess some inductance due to their shape. The capacitance of an antenna originates from the electric fields formed between different parts of the antenna or between the antenna and nearby objects. Um, in antennas, there are two kinds of resistive elements that are used for modeling the behavior. One is the loss resistance. Um, so both of the resistive elements account for the um, loss of power from the antenna, whether it's through heat or radiation. So the loss resistance accounts for the power dissipated as heat within the antenna itself, and this includes the ohmic resistance of the antenna's elements. Radiation resistance, on the other hand, um, represents the effective resistance of the system, taking into account the power dissipated by radiating it uh, by radiation of the electromagnetic waves. RLC circuits have the resonance property when their inductive reactance and the capacitive reactance are equal in magnitude. When they are equal in magnitude and opposite in sign, so when they cancel out, um, at this resonant frequency, the antenna's impedance becomes purely resistive. So, um, an antenna is connected to a transmission line. Uh, there is a chance that reflections may take place at the interface of the uh, two elements. This is analogous to the reflections that take place in visible light between two mediums. Um, and the reflection coefficient, which uh, is the ratio of the reflected um, voltage to the incident voltage. The expression for that is given on the slide, and it is analogous to Fresnel's equation, where the reflective coefficient depends on the refractive indices of the two media. The characteristic impedance of a transmission line is usually 50 ohms, and one way in which the reflections that take place between the two elements is quantified is the standing wave ratio. So the standing wave ratio is a measure of the amount of power that is reflected back um, through a transmission line due to impedance mismatch. Uh, It's the ratio, as is shown on screen, of the maximum to the minimum voltage, and an SWR of 1 means the that there is no loss of power, while a higher ratio indicates a higher loss of power. And uh, the and reflections can not only reduce the power transmitted, but uh, they can also cause excessive heat and may damage the transmitter. So, um, so to prevent the effects of uh, reflections and power loss, it is necessary to match the impedances of uh, the the antenna and the transmission line. And as is evident from the expression for the reflection coefficient, um, the reflection coefficient is uh, zero when the impedances are equal. And these three method and these three are common methods used for impedance matching. So matching networks involves using inductive and capacitive elements um, to um, match the impedance of the antenna and the transmission line. A quarter wave transformer is uh, the use of a short um, length of transmission line, uh, which is a quarter wavelength, quarter times the wavelength, with an impedance that is equal to the geometric mean of the antenna and the transmission line. This causes it to gradually transform one impedance to the other. Uh, an autotransformer is a single coil that, in this case, adjusts the inductance as required to adjust the impedance of the antenna. Another parameter that um, categorizes that is necessary to study antennas is the bandwidth. So the bandwidth is the range of frequencies over which an antenna operates satisfactorily, or it fulfills certain criteria depending on their application. So antennas can have a radiation pattern bandwidth, which is the frequency range over which a specific beam width or side lobe level or polarization are maintained. They also have a gain bandwidth, which is the set of frequencies over which the gain uh, a gain exceeds a certain threshold. Um, they also have an input impedance bandwidth, um, which refers to the frequencies, where the standing wave ratio is less than a particular level, usually minus 10 dB. Polarization. Um, so, the polarization of an electromagnetic wave is the direction of the electric field vector, and it is necessary for the polarization of an antenna to match the polarization of the signal to avoid signal loss. There are three types of polarizations as shown in the figure: linear, circular, and ellipse. Um, Matching the polarization is necessary for reducing signal loss since the received power is directly proportional to cos square x, where x is the angle between the polarization of the antenna and the polarization of the wave. Uh, as an example of the polarization of the signal loss that arises due to polarization risk, when a left-handed circularly polarized wave interacts with a right-handed circularly polarized antenna, there is no signal received. And when a linearly polarized antenna interacts with a circularly polarized signal, it always results in a 3 decibel loss. So, focusing on circular polarization occurs when there are two directions of the electric field which are orthogonal to each other, and each one has a 90-degree phase shift. They are extensively used for satellite communications since they are less susceptible to losses when the receiving antenna's orientation does not match the source. The Earth's atmosphere can cause effects such as depolarization that can lead to signal degradation, and circular polarization is used because it is more resistant to these effects. The Faraday effect, due to the Earth's magnetic field, can rotate the polarization of signals. Again, circular polarization is not as affected by this as linear polarization. Another, another way in which polarization is used is for interference mitigation, where two different polarization directions are used to reduce interference between the signals. For example, for circular polarization, right-handed circular polarization and left-handed circular polarization can be used to reduce interference. Let's take a look at polarization in some antennas that we often encounter. In FM and AM radio antennas, uh, in FM and AM radio, the polarization used is vertical linear, which matches the orientation of the car's antenna. TV broadcasts use waves with horizontal linear polarization, and this is done to reduce the interference that arise from man-made objects like buildings. Phones use dual polarization, which is polarization along two axes, because phones are often used at various different angles. Um, Over to Srikiran now.
So the Wi-Fi antennas on your phone must be able to receive signals regardless of the direction the router is at relative to the phone. On the other hand, a radar system needs to have antennas that are more sensitive to a particular direction so that you can tell that there's an object in that direction. The parameter we use to quantify the directional concentration of an antenna's radiation is its directivity. The directivity is given by the ratio of the radiation intensity in a particular direction to the radiation intensity averaged over all directions. So you'll notice that the average radiation intensity is just the total power radiated divided by 4 pi. So that gives us another formula for calculating directivity. Also notice that an isotropic antenna would have a directivity of 1 since it radiates the same power in all directions. the average power is equal to that power itself. So directivity is also a measure of how much more power is radiated in a direction relative to an isotropic antenna. Here you can see some other units which are used for directivity. If the unit is dBi, it is so whenever you're using a decibel unit, you'll have a reference value to which you'll be comparing your measured value. If the unit is dBi, the reference value you're using is the directivity of an isotropic antenna, which is 1. If the unit is dBd, the reference value you'll use is the directivity of a perfect half wavelength dipole antenna, whose directivity is 1.64. Also note that if the direction is not specified, the directivity is taken in the direction of maximum radiation intensity. Here we have an example for the procedure to calculate directivity. So first, you'll notice that the direction is not specified. So what we need to calculate is the directivity in the direction of maximum radiation intensity. And if the radiation intensity is given by B naught sine cube theta, you'll have the maximum radiation in at angle theta equal to pi by 2 or 3 pi by 2. So Umax, or at least it's the modulus of U is the maximum of the modulus of U is B naught. And the power radiated is calculated, can be computed through this integral over here, which comes out to be 3 B naught pi square by 4. And then we use the formula D equal to 4 pi U by total power radiated, which gives us a final answer of 1.69. So this is the procedure you would use to calculate the directivity of an antenna. And these are the typical directivities of other antennas. So you'll see that a short dipole antenna has a directivity of 1.5. A half-wave dipole has a directivity of 1.64. A horn antenna has a directivity of 10 to 100. So it's much more, so it's 100 times more directional than an isotropic antenna. Whereas a dish antenna has a directivity as of 10,000, of 10 to 10,000. So its radiation is around 10,000 times more directional than an isotropic antenna. Now that we have talked about how the antenna directs its energy, the next question we must raise is how much of the power that we feed into the antenna actually gets radiated? Some of the energy input to the antenna is reflected back due to impedance mismatch between the transmission line and the antenna. Some of the energy is again lost due to resistance of the conductors. Further, since we use some material to, so the substrate, the PCB substrate which we mount our antenna on, can also absorb some of the power, which is called dielectric loss. There is also a phenomenon called the skin effect, where the alternating current in a conductor becomes distributed such that the current density is largest at the surface and decreases exponentially with depth. So you can see here in this picture, the brightness of the color is the current density at that point. So it's highest at the surface and it decreases as you go down. This delta is called the skin depth, which is equal to the depth at which the current density becomes 1 by 0.37 the surface current density. As the frequency of the alternating current increases, the skin effect also becomes more pronounced. So yes, the skin depth would keep decreasing, basically. Thus, for a high frequency antenna, increasing the size of your conductors may not reduce the ohmic resistance as much as you think it would. The radiation efficiency is the ratio of the total power radiated by an antenna to the net power accepted by the antenna. This parameter takes into account the losses due to the conductivity of uh, the the conductivity of whatever conductor we use, as well as dielectric absorption, but excludes losses caused by impedance mismatch. The total efficiency takes into account the impedance mismatch as well. So the total efficiency is the radiation efficiency multiplied by this factor, where 1 minus mod gamma square is the power that is basically a measure of how much energy is left after reflections. Earlier, we looked into directivity. However, since it compared the radiation intensity in a given direction to the total to the total power radiated, it doesn't give us an idea about the efficiency of an antenna. Combining these two parameters together, we have a parameter called the gain. The gain describes how well an antenna converts input power into electromagnetic waves in a particular direction. It is defined as the ratio of the intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated at 100% efficiency by an isotropic antenna. And here we have two kinds of gain. The absolute gain only takes into account conductive and dielectric losses. So in this formula here, you will have the radiation efficiency, G equal to radiation efficiency into directivity. The realized gain also takes into account mismatch losses. So instead of the radiation efficiency, I will use the total efficiency. And similar to directivity, when the direction is not specified, we take the gain to be in the direction of maximum radiation intensity. Here we can see the gain of dipole antennas at various lengths. So dipole antennas are resonant not only at the half wavelength, but also at integer multiples of half wavelength. And here you can see the values of gain for okay, the YouTube stream starting again. Just give it some time. Hello. Yeah, that should be it. Sorry. So I'll just start from, okay. So we can make use of overtone resonances. You guys can hear me, right? Okay, I'll assume you can. So you can make use of overtone resonances to allow an antenna to resonate at multiple frequencies. So if you have some, so you have the low and high VHF television bands. The low VHF television band is centered around 65 megahertz, and the high VHF television band is centered around 195 megahertz. So an antenna, which is a dipole antenna, which can resonate at the low VHF band, which is 65 megahertz, can also resonate at the high VHF television band, which is 195 megahertz. You'll notice that it's three times the 195 is three times 65. So that was audible, right? Hello.
Yeah.
Okay, okay, fine. Uh, I guess the YouTube stream is still bugged actually. So, yeah,
Is it
fine.
just because of the delay or?
Yeah, it's the delay. Fine, fine. No problem. It's working. Thank you. Sorry about this problems, guys. It wasn't supposed to happen. All right. So now we come to loop antennas. As the name suggests, loop antennas consist of a coil of wire connected to a source for transmitting or a load for receiving. So large loop antennas usually refers. So again, in loop antennas, you can have resonance, but this time current would start over here. Let's just say I have some current at some phase over here, and the total perimeter is lambda. So once it goes around and comes back, it has traveled through one wavelength, and its phase difference would just be 2 pi. So the current is in phase, and it would add constructively. You would get like standing waves and fixed nodes and antinodes, similar to the dipole case. You'll have a maximum current at the antinodes, and you'll have maximum efficiency at when the perimeter is equal to n lambda. And also, the resonance does not depend much on the shape, since all that matters is that by the time the current has gone through the entire loop and come back, it should travel one wavelength distance. But you should still avoid excessive meandering or sharp bends, because the sharp bends may cause localized increases in current density, which can heat up which can heat up your element and increase the resistance. And the the bends and the meandering and basically the geometry of the loop, it would still affect the way the electric and magnetic fields combine. So you may end up with distorted or weaker fields. And unlike a dipole antenna, the polarization of a resonant loop antenna is not determined by the orientation of the loop itself, but it also depends on the placement of the feed point. If a vertically oriented loop is fed at the bottom, then its radiation will be horizontally polarized. Feeding it from the side will make it vertically polarized. This gives loop antennas some flexibility in design. So now we come to small loop antennas. These are much smaller than the wavelength. And again, similar to the short dipoles, you can't get resonance over here. Uh, their efficiency is less, and they are usually used as a receiving antenna and around 15 megahertz, because around 15 megahertz, the noise from the circuit itself, as well as the background noise, is minimum. So you can amplify the signal without degrading it a lot. Another interesting thing about small loop antennas is because of the radiation pattern, you can see over here, and also from this from the equations of the fields, that uh, you'll have a null wait, yeah. So the radiation pattern is such that uh, the it receives the weakest. I mean, the radiation pattern is intensity is weakest at theta equal to 0 and theta equal to pi. So you have two ends of the uh, loop. I mean, two ends of the radiation pattern where the radiation intensity is 0. Uh, and these two directions are perpendicular to the plane of the loop. So in direction finding, you can rotate the loop antenna such that uh, the direction of these 2 points points towards the source, since at that direction you'll be receiving minimum current in your loop. However, you've only narrowed down the direction to two different directions, which is either that the plane of the antenna is facing the source or it is facing away from the source. So to actually find the point, you need to use some other methods. One method is to use another loop antenna, or just move to a different position and take a measurement of the angle from there, and then triangulate the source. Another important feature of loop antennas is that they produce strong magnetic fields and relatively weak electric fields. This has an interesting application involving the human bodies. So the human body has a high permittivity, which means that it interacts strongly with electric fields, but it has a low permeability, which means that it interacts less with magnetic fields. So the proximity of a human body does not affect the performance of a loop antenna, and it can be used in wearable devices or medical monitoring devices. Okay, So now we are done with loop antennas. And so first in this picture, you can see a sailor blowing his bugle into an acoustic megaphone to make the sound louder, to wake up his uh, to wake up the other soldiers. An acoustic megaphone makes the sound entering it louder, not by adding energy somehow, but by improving how efficiently the sound travels through the air. So this is done by increasing the directivity of the sound as well as impedance matching. Acoustic impedance is just a measure of how easily the sound can travel through a medium, similar to electric impedance. The gradually widening flare matches the impedance of the bugle to the acoustic impedance of the air, and all the sound is more efficiently directed towards a particular direction. The bugle itself has a horn structure where the impedance of the uh, air in your mouth is matched to the impedance of the surrounding. Also note that the megaphone does not treat all frequencies equally. It amplifies higher frequencies much more than lower ones, which results in voices sounding unnatural. The same principle behind acoustic megaphones is used in horn antennas. So here you can see that we have a flared horn similar to the megaphone, and this allows for the impedance to be gradually matched from the waveguide to the impedance of the surrounding. If there were, if we didn't have this horn, uh, the sudden end of conductive walls will cause an abrupt impedance change, and because of this, you will end up having reflections. And actually, here it reflects back to the source, and it's not like useful reflections. You'll have like a significant portion of the radio wave reflected back to your source. Horn antennas are mostly used at high frequencies, and they have a directional radiation pattern with a high gain, around 10 to 20 decibels higher than an isotropic source. And similar to the megaphone, it amplifies, sorry, the gain of the horn antennas increases as we increase the frequency of the radio waves. And they also operate over a broad bandwidth. And so here you can see a horn, an exponential horn. So this is the horn which gives us the most efficient impedance matching. So this results in the minimum amount of signal loss, and we use these in applications like radio astronomy and in satellite antennas. However, these horns are harder to fabricate. So for common usage, we use normal horns like this, pyramidal horns. Yes. Here you can see the radiation pattern of the horn. You can see that it is indeed much more directional. You have one entire lobe and a few other pointing towards one direction, and a few other side lobes pointing slightly away. And horn antennas are used in radio astronomy because the directional pattern of the horn antennas allows the astronomers to pinpoint a region of the sky from where the source, to pinpoint a region of the sky where the source can be located. And the horn shape also maximizes efficiency, which is crucial when you're trying to detect faint signals from space. The broad bandwidth of horn antennas also allows for high data transfer rates. So they're used in satellite communications, and horn antennas are also used as feed elements for parabolic reflectors since they illuminate the dish uniformly and efficiently, ensuring maximum gain and minimum wasted radiation. Thank you. And now I will be handing it over to Kirtana, who will be covering a few more types of antennas, such as the helical and oh wait, yes, I forgot about this. So this is the horn antenna, which was used to discover the CMB, as Kirtana mentioned earlier. You can see that it had their horn is actually quite large, and it allows for very slow and very gradual uh, matching of the impedance from the source to the surrounding. So that's all for me. I will now be handing it over to Kirtana, who will be covering a few more types of antennas.
Thank you.
Okay, the presentation just ended. Oh, wait, give me a second. I'll just start again. Yes.
Thank you. Let's take a closer look at helical antennas. So, a helical antenna consists of a single metal wire wound as a helix. Uh, some of its geometric parameters which influence its properties are its circumference, its pitch, and the number of turns. So the pitch can be measured either as the pitch length, which is the distance between two consecutive loops, or with the angle that the wire forms with respect to the horizontal. So the helical antenna has two modes of operation, which are the normal and the axial modes. For the normal mode of the helical, for the normal mode of operation for the helical antenna, the circumference has to be much less than length, and the pitch also has to be very small. And in this case, the currents in all the turns are nearly in phase, and it behaves like a short loop array. As you can see from the figure, the gain pattern is nearly toroidal, and it produces linearly polarized light, and it is a narrowband antenna. In the axial mode, the axial mode was discovered by um, wait, is the image visible to everyone? Okay.
Yeah, we can see.
Okay. The axial. Okay. I wasn't able to see it earlier. That's why I asked. The axial mode of the helical antenna was discovered by John Cross, and it occurs when the value of the circumference is comparable to the value of the wavelength. Um, there's also a criterion for the pitch of the antenna. In this mode, the antenna radiates strongly along its axis, as you can see from the uh, figure, and the phase of the current increases by a regular interval with each turn of the helix. Uh, this acts as a wideband antenna with moderate gain. Let's take a look at some of the and one interesting um, point about the axial mode of the helical antenna is that it produces circularly polarized light, and this uh, leads it to have a lot of applications, which are mentioned here. So the applications revolve around the circular polarization that is produced. Um, and they include satellite communication, GPS, and telemetry links. They're also used in advanced RFID and IoT devices. And helical antennas are also used in radioastronomy to detect pulsars as well as emissions from Jupiter. Um, and the image shown on the slide is uh, of the Nance decameter array, which uses an array of helical antennas to observe radio emissions from the Sun and Jupiter. Let's take a look at some of the properties of helical antennas. Um, so, the half power beamwidth is a measure of the angular width of the main lobe of an antenna's radiation pattern, where the power is at least half of its maximum value. So, taking a closer look at its properties, um, we can say that we've seen that the circumference affects whether the antenna radiates in the normal mode or the axial mode. An increase in circumference causes a decrease in the half power beam width, and it also affects directivity. The spacing between turns or the pitch angle determines the phase difference between turns, and this affects the directivity and bandwidth. A small pitch may result in a lower bandwidth but higher directivity than a large pitch. Increasing the number of turns increases the antenna's effective aperture um, and its gain. The half power beamwidth varies inversely with n. So, taking a look at the bandwidth of the antenna, the axial mode helical antenna operates as a traveling wave antenna. This means that, unlike a resonating dipole, the current distribution in the antenna is not a standing wave. The ratio of the highest to the lowest frequency of an axial mode helical antenna can be of the order of 1.7 to 2, making it a broadband antenna. Let's take a look at the circular polarization in a helical antenna. The circular polarization of an axial mode helical antenna arises due to its geometry with the rotation of the electric field vector. The electric field can be thought to have two orthogonal components: a horizontal polarization due to the currents in the loops, and a vertical component due to the helical progression. The helix has a fixed phase shift of around 1 lambda per turn, and this ensures that these components have a 90-degree phase difference, resulting in circular polarization. A right-handed helix produces right-handed circular polarization, while a left-handed helix produces left-handed circular polarization. Over to Vatsal, who will explain about microstrip or patch antennas.
Yeah, hi, am I audible?
Yeah,
Okay. So, in a lot of places around us, we realize that there's a lot of antennas present right now. So, but the most widespread sort of antennas are present in our digital devices. So, the kind of device that you would be using to watch the stream right now would have maybe not just one but multiple such microstrip or patch antennas. These are basically antennas that are so small that are they can be printed out on a PCB. They are very compact and they don't have any moving parts at all. So these are, as the name suggests, they are basically strips or patches of a conducting, say, copper layer on a PCB substrate, which is a dielectric, for example. And these are usually very small, so small that these usually pick up not radio waves but also microwaves. And as we know, most of our advanced communication, which is say 5G or even a bit of 4G, happens usually mostly in the microwave region rather than the RF region. So that's why these have been become very popular recently, and because they're very easy to fabricate sometimes, and they are very easy to reproduce. And again, they're not huge, cumbersome things. As you would have seen, like a lot of years ago, there would be those old radios or old telephones in which you had to, like, you had a retractable antenna which you had to pull out, and it would become a whole big thing, and that would receive our signals for us. So that sort of size is required for those wavelengths. But as we evolve technologically, the wavelengths that we use for communication have become smaller, and thus the antennas also have become so small that they can fit on the palm of our hand. Um, so these are basically, as I said, patch or strips of metallic substance on a dielectric base. And radiation here happens similar to how it happens in a dipole antenna. It happens characteristic of its size. Now, one difference with other antennas is that the dielectric around all other antennas is usually air, but for this case, it's a dielectric on the PCB board itself. So it will have different permittivity numbers. So the wavelength itself, the effective wavelength, will be different due to diffraction effects of light itself. And so that's why we need a shorter antenna, because wavelength will be shorter there. Also, because these are finite in size, and they have something called fringing effect at their edges. So most of the radiation occurs uh, because of the interaction at the boundaries of substances. So in your electromagnetic study, you would have noticed that almost all equations are nice and smooth when we are talking about a bulk material, and whenever we come to an edge, we sometimes use different kind of equations which are called boundary equations or something. So, um, the radiation or receiving in these antennas occur at the boundaries due to fringing of EM fields, and we can think of this as resonant cavities. So, if somebody would know about how lasers work, they have a certain cavity from which we can get a resonant effect. And because these are also in a way different sort of medium inside of a dielectric medium, then there's standing waves that form here also, which radiate out and give out the radiations. So in a way, they can be treated as transmission lines. So the transmission lines that we see around us, the wires that we have, or the USB cables that we're using, they all have their own intrinsic capacitance, inductance, and resistance. And as we have learned in our 11th grade, that an RLC circuit will resonate. It will release out electromagnetic radiation, and it will lose its energy. So in a similar way, this will also behave like an RLC circuit, radiating out energy in form of EM waves, maybe radio waves or microwaves. So these are usually used in almost all of our digital technologies which are connected to Wi-Fi or internet or Bluetooth, even cellular devices, sometimes NFC also. A lot of You would have seen some business cards or ATM cards would be tap to pay. So they use NFC technology there. And even our IATM ID card is that you can tap it and it authorizes stuff. So it has an antenna inside, which is just a coil. It will pick up power from the device that is radiating, and it will send its own characteristic signal inside of that to back to that device, which will help it authenticate stuff. So um, in case of ATM cards or even our own ID card, there is a layer of security after the NFC, so it's more secure that way. And if somebody would have used some development boards like Raspberry Pi or something, you would have seen some metal squiggly lines on a black background or something. Those are antennas again. So because Raspberry Pis can be connected to internet, these small, very short antennas can do that work passively. So one disadvantage of these is that they are not very efficient because they're very small and very compact, usually very simple designs, and they have narrow bandwidth, so they can't pick up almost all the radiation that we throw at them. But that serves as an advantage also. They are very small, compact. They are very easy to manufacture. They are very cheap sometimes, as they are printed directly on board. They don't need additional hardware, and they can be made using almost normal PCB printing technologies. And most of our phones will have multiple of these antennas throughout its structure. So they'll all be targeted. They'll all be targeting different technologies. So there'll be a Bluetooth antenna. There'll be a Wi-Fi antenna, and you would have seen some in some metallic phones. You would have seen a cutout usually, which is not a button. You can't really press it, but it will be different from the metallic frame. So that will be an antenna cutout. So it will be a non-metallic substance so that it does not block the EM radiation, and just behind that will be an antenna, which will help pick up our cellular connection or Wi-Fi or something. Yeah, I'll give it back to Kirtana for the next topic.
Thank you. Um, let's take a look at parabolic reflector antennas. So a parabolic reflector antenna consists of a metallic reflector shaped as a paraboloid of revolution. Um, yeah, sorry. Um, so a parabolic reflector antenna consists of a metallic reflector shaped as a paraboloid of revolution and a feed antenna, which is usually a horn or a dipole, at its focus. The dish may be a solid or a mesh with holes much less than lambda. Parabolic reflectors uh, are used in areas where high directivity is required. So to understand how a parabolic reflector works, we can recollect a principle from geometrical optics, um, which states that uh, when light waves um, when light waves which are parallel to the principal axis uh, get reflected from a parabolic mirror, they converge at the focus. The same principle is used by a parabolic reflector. The rays passing through the focus become parallel to the axis after undergoing reflection. Um, so, uh, so a collimated beam with a planar wavefront is produced. And for receiving signals, a plane wave traveling along the axis of the parabola converges at its focus, and this maximizes the signal received by the feed antenna. Uh, this affects the gain of the parabolic reflector. The gain of a parabolic antenna depends on its aperture size with respect to its wavelength and on how uniformly it's illuminated. A result of aperture antenna theory is that uh, the gain is given by the equation on screen, where eta is the aperture efficiency, which is the ratio of the effective area of the aperture to its physical area. The effective aperture area is the area of an ideal antenna that would capture the same power as the real antenna does. This expression indicates that an increase in the aperture size results in an increase in directive gain, and this can be understood intuitively since a larger dish collects and focuses more energy. The half power beamwidth is inversely proportional to the aperture diameter uh, and is given by the expression shown on screen. Um, as the diameter increases, the, the beam width decreases, which is consistent with the increase in gain. Larger dishes produce narrow beams, sometimes of the order of arc minutes, which is why parabolic reflectors are used for, long range uh, communication and for astronomy. One thing to be noted is that if the dish size were comparable to lambda, the diffraction effects would become significant, and that may even cause the gain to decrease. Let's take a look at some of the applications of the parabolic reflector. Um, Parabolic reflectors are used in a wide range of areas that require high gain or directivity. They are used in satellite communication because of their high directivity and their ability to collect weak signals effectively. They are also used extensively in radars. They are also used as radio telescopes and are often used for deep sky surveys. They may also be used with pulsars at the feed to uh, observe with sorry. They may also be used to observe pulsars with helical antennas at the feed. Over to Vatsal.
So now we come across a very interesting aspect of radio antenna telescopes is the case of phased antenna arrays. So in a lot of applications, we need a very highly directive antenna. For example, if I have a very small point source somewhere, and which is faint, for example, then I can't just point a dipole antenna at it, for example, and because it'll take signal from all the directions, almost all the directions, and my signal to noise ratio will be very less. So I'll be receiving noise from a lot of other directions, which I don't want to. Sometimes, even if there is not a lot of noise, if I want to pinpoint the direction from which the signal is coming, then even then I can't do that because in almost every direction I'll pick up some noise and some signal, and I won't be able to pinpoint exactly where the signal is coming from. It's like seeing through a very fuzzy set of eyeglasses. You can't actually pinpoint where the object is placed. So, in a lot of practical applications, we need high directivity antennas. A problem that comes across is that sometimes making such high directivity antennas may not be very feasible because they involve either very technologically advanced materials or very involved designs, which may make them maybe more expensive, more complex, and sometimes even impossible to fabricate for our application. Say, even if we are able to make such an antenna, then arises another problem is that what if I want to look at any other direction other than that particular specific direction? So one way of doing this is how old navy ships used to do this. You would have seen this right hand side diagram in some movies or some pop culture reference somewhere, and it basically reflects how a radar would like spin around in a with a huge motor on top of a navy ship, for example, to locate a small source, which may be a fighter jet, for example. And if that fighter jet is coming towards the ship, then it'll that spot will on every pass it'll appear closer to us, or if it's going away, then it'll appear farther away, and that gives us a sense of where the object is by rotating around an entire antenna array. So this is a good method as it accomplishes what we want to do. But the problem is that the refresh rate as such, knowing how fast the object is coming or how frequently we can get that data is very slow, because there's a physical limitation to how fast we can rotate a huge, highly directive antenna. And again, uh, using motors and controls for the motors and having all those moving parts may become cumbersome. They require maintenance, and they're highly expensive sometimes. They need to be very precise in a lot of cases, and so these all give a lot of constraints to this method of localizing objects. Now, these are almost all very textbook definitions of where electronics can help us achieve our motives, and mechanics where mechanics would usually fail. So, as we don't need a lot of moving parts, we need to be as simple as possible. We need to be as quick and fast as possible, as reliable as possible. And that's where electronics comes and meets antenna theory. So, this is how a phased antenna array construction would look like. Say, imagine you have a line of antennas which are all equally spaced, for example, and they are usually simple antennas. They don't need to be very complex, very difficult to make antennas. Usually they are dipole antennas. Sometimes they are dish antennas, the parabolic reflectors that we talked about. To connect it to them are electronically controlled phase delays. These are, for now, let's consider them as black boxes. They are electronic devices which can control the phase of the input electrical wave. So if I say put in 5 volts to them, they'll give out a phase delay of 30 degrees. If I say put 10 volts, they'll give out 60 degrees, something like that. The point of the matter is that I can control very easily the amount of phase delay that each of them provides very nicely with electrical signals, which I can create very easily. And finally, there's an adder, which is again an electrical circuit that just adds signals. Mathematically, you can just, they are represented by a plus sign. So if I have two different signals, an adder will just A plus B them. They'll just add the signals. It's not very difficult to understand here. Now, say we want, the whole motivation of all of this was that we need directivity without compromising a lot of complexity, and also we need control over that directivity. So let's imagine this scenario in which we have n number of antennas. They are all separated by a constant distance d between them, and we want to look at a particular part of the sky which is theta degrees from the horizontal. So fine. Let's look at the picture on the left. So the rightmost antenna there will receive the light or the electromagnetic radiation head on. Like there will be no delay in that. The next one, in relation to the first one, will have a path length difference of d cos theta. Path length difference is basically just the difference in how much the ray has to travel in one scenario and in another scenario. So the same radiation will have to travel d cos theta more to reach the second antenna, as you can see very clearly in that image. In the third antenna, that path length difference would be 2d cos theta. The third will be 3d cos theta, fourth, sorry, and so on. So if I have n antennas, the last one will have a path length difference of n minus 1 d cos theta. Fair. Now, as is true with any sort of waves, any path length difference will create a phase difference. So, as you would have learned in your waves course, that a 2 pi phase difference comes with a path length difference of lambda, where lambda is the wavelength. A pi phase difference comes with lambda by 2, and so on. A lambda by 4 will create pi by 2 or something. And so, d cos theta will create a phase difference of 2 pi by lambda times d cos theta. A fancy way of saying 2 pi by lambda is just k, which is the wave number. So the phase difference that arrives at the second antenna relative to the first antenna would be k d cos theta, as it's given in the fourth line. So the first three lines, let's recap through all of that. So let's say the first antenna receives a radiation of amplitude A. Usually in our waves courses, we define wave equation as A cos kx minus omega t plus some constant theta, for example, which is the phase difference. Now, there's a trick in complex numbers that we can bring this theta out and say that this wave equation is the real part of A e power iota theta times cos kx minus omega t. So basically what we can do is that we can put this A cos kx minus omega t as one term, which I have defined as capital A here. And we can define this additional phase term as e power I capital phi, where capital phi is the kd cos theta, which we defined just a few minutes ago. Now, say we just forget about those electronically controlled phase delays, and we just have a series of n antennas whose outputs are added together, and we just read them off. So the net signal that we'll receive would be a times 1 plus e power I phi, 1 plus e power I 2 phi times, and so on. So which is given in the sixth line here, yeah, in the right hand side. And so it is very evident that this is a geometric progression whose sum has a known formula which we can put in. And at this point, we define something called an array factor. It's a very important thing in while we're discussing antenna arrays. It's a tool that helps us understand how antenna arrays work, and it's a very nice tool for understanding how what is the net power that I gain at this particular angle, for example. So we'll all come to that later. So array factor is defined as the net signal that I receive divided by the total number of antennas divided by and the signal that I receive at each antenna. So in a sense, it's independent of the number of the signal that I receive, the amplitude of signal, and it's basically a measure of how the antennas are arranged in physical space. So if we can put that equation in and solving that the sum of that geometric progression, we'll get array factor is equal to 1 minus e power iota n phi divided by n times 1 minus e power iota phi. This is a very well known geometric progression sum equation, and it's very fine till now. Now we can do a very nifty trick from again complex variables that in the numerator we can take e power iota n by 2 phi outside. So that leaves us with e power iota n phi by 2 minus e power iota minus n phi by 2. Or no, the opposite, e power minus iota n phi by 2 minus e power iota n phi by 2. Similarly, from the denominator we can take out e power iota phi by 2, which leaves us with e power minus iota phi by 2 minus e power iota phi by 2. So it looks a lot like the sine theta equation in complex equation. So sine theta can be defined as e power iota phi iota theta minus e power minus iota theta by 2 by 2 iota. So we can plug that in right here, and we get the equation in the third last line. So there's some complex term times sine n phi by 2 over n sine phi by 2. So in all of the situations, we have come up with this simple looking equation for an array factor. Now you would have noticed that it does not involve any mention about the amplitude that one antenna receives or even the radiation pattern of that antenna for that matter. Let's array factor in general is independent of that. So if we take the absolute value of this, because usually in signals when we measure them, we can't really measure that phase so well. So we just put a voltmeter there and just find out the voltage that's being outputted, and we take the absolute value of this and we get sine n phi by 2 over n sine phi by 2. Now this may seem like a very peculiar equation, and it kind of is. It's not a very natural equation that occurs in a lot of other places. So how about we plot it? Usually when we see new equations, we try to plot it. We'll plot it with theta, but we know that capital phi is very closely related to theta, as phi is kd cos theta. And we'll do one more assumption here. Let's say d is equal to lambda by 2. The separation between two consecutive antennas is equal to the wavelength divided by 2. It's equal to half the wavelength. Now so if we plug that back in capital phi, we get kd cos theta, where k is 2 pi by lambda and d is lambda by 2. So kd would be pi, and so capital phi will be pi cos theta. So the meaning of all of this is that phi is very closely related to theta. Now we can plot this array factor term easily on a graph, and then we get the following graph. So in a way, we also know that array factor is very closely related to the amplitude that we receive at that particular theta, for example. So we know that array factor is dependent on phi, so it is also dependent on theta. So how we point our so we can get higher gain in a certain particular direction and lower gain in some other particular direction. So as the graph on the right suggests, that array factor is not constant throughout for all theta. So let's just take one of the graphs. Let's take capital N equal to 2. So just two antennas side by side, they are separated by lambda by 2 distance, and I just add the terms that they get, add the signal that they get. So here we can see that there's a very clear high gain for theta is equal to zeros. So we see that when the source is like at theta is equal to 0, we'll get a much stronger signal when rather than it's at say theta is equal to 180 degrees or minus 180 degrees. So the x-axis at the bottom is basically just the radians, angle in radians. So, and one more thing that we notice is that when we keep increasing the number n, which is the number of antennas in that array, the radiation pattern somehow becomes more narrower. So the whole concept of directivity becomes even stronger. So there's only a very small theta range around 0 where my gain will be the highest. So I'll receive maximum of my signal from that one particular small area only. So in this way, without using any complex structures, we have created highly directive antennas whose directivity will keep on increasing if we increase the number of antennas in that array. So again, that is a trade-off between how much you want to do construction and how much directivity you want. So yeah, so now one thing is done is that we have created very highly directive antennas. Um, but the other problem still remains that how do we steer these beams? Now comes the electronically controlled phased array part. So if I have if I devise a method in which I can put say alpha degrees in the first phase delay, 2 alpha in the second one, 3 alpha in the third one, and so on, then my total net capital phi term will look something like this: kd cos theta plus an additional alpha term which I can control myself. Now, a direct consequence of this is that we are shifting the array factor graph laterally in theta. So the peak where maximum directivity occurs or the maximum gain occurs in array is shifted in theta. So in the right hand graph, you can see that it's plotted for some particular n, for example, phi, I guess here. And we see that changing alpha can actually change the position of maxima of gain. So for different theta, electronically we can control where the maximum gain occurs. So this whole concept of changing the beam where the highest gain of the beam occurs is called beam steering, and it's a very important concept in array factor engineering. So a very easy, simple way to visualize all of these graphs is with a bit of coding. So I'll just share my screen here. Yeah. Is the Colab notebook visible?
One second, I'm doing that part.
Yeah, sure.
Yes, now it should be visible.
Sure. So usually, as they say, so all of this, the motivation to all of Python here is not to look into Python as such, but the main motivation to this is that Python is a very good tool to visualize graphs a lot of times, and we can work around very easily, interactively sometimes. So this is, so people who are familiar with Python know that this is usually done in almost all the programs. This is importing some certain libraries, which has no consequence physically with our demo, so we'll just skip over that. This, as you can see, is the array factor equation. We've just not done the addition here. It's just in the sigma term. And here is the familiar equation that we derived in the last slide. This is a computer program that can find out the array factor for a particular theta, as array is theta dependent. It's for a particular number of antennas situated at d distance apart each, and this is the additional alpha term that we are adding, the phase shift in degrees. And if we run this, Now we can set up our own visualization tools. And so this is, again, this is also not, this is just Python, and it just helps us to visualize everything. So I think did it run? Yeah. So these are two graphs. The left hand side graph is what we saw in the slide also. And the graph on the right hand side is usually how we see in real life. So we don't usually see angle as a linear scale. We usually look into it like a protractor type of way, and it's a polar plot usually. So the diagram on the right may seem familiar to some people. It's the cross section of a radiation pattern. So it's basically just this left hand side graph um, shaped into a semicircle. So it kind of looks like the radiation pattern thing that we saw earlier. Now, one good thing of Python is the interactability. Say, if I want to steer this beam now, if I just put in an arbitrary random value of alpha, say 50 degrees, we see that the whole graph has shifted to a certain direction. So instead of having our maxima directly like vertically upwards, where our maximum gain occurs, just by controlling one small parameter, which is alpha, which is in a real life just an electrical signal, we can steer the whole maximum gain beam to any angle that we want. So if I say, if I want to steer it in another direction, say I put minus 85 degrees, we see that the beam has steered to a different direction. And so this alpha is very easy to control electronically. And the whole premise of this is that very easily, without any moving parts, just electronically, we can control the angle of the beam. Now, this can be done very quickly with modern electronics. Digital circuitry is so modern that we can do this almost instantaneously, and we can scan a lot of huge part of the sky. And so that whole rotating around of the huge radar antenna is now almost obsolete. Modern fighter jets are so capable that they can track multiple objects at the same time. So they use a similar sort of technology also. So now, one more interesting thing that we can see here is the effect of number of antennas that we have. So this graph is plotted for array and 5 antennas in that array. So if we reset the angle again, yes, and then say we increase the number of antennas to 12, 13. So one consequence that you can see from the right hand side graph very clearly is that the half power beam width, or the width of the lobe, has shrunk down a lot. So in a sense, our directivity has increased so much from the 5 antenna case. And so having higher additional antennas, sometimes antenna arrays used for radio astronomy use hundreds of antennas. For example, there is an antenna array in India that has, I think, so many antennas that it can pinpoint the accurate part of the sky in just like a few degrees, a couple of degrees. So imagine the whole sky in all of the 180 degrees of the sky, and just by passively changing without any moving parts, we can pinpoint where the radiation is coming from in like 1 or 2 degrees of the sky, which is amazing. And along with that, we find some other things. So in this left-hand side graph, you could see that there are a few more lobes that are coming in. So these are called side lobes, as they are beside the main lobe, main gain pattern of the antenna. And these are also places from which radiation can be received, but they are usually very low in power, and we usually so in antenna arrays they don't play such a huge role unless we are working with some very weird angles and they come up like this. So just as it was mentioned before, increasing the n will do this. Decreasing it to say a value of 2 will create no side lobes, but a very wide antenna pattern, which is sometimes not nice for us. Now, one more thing that we can control during our construction is how far apart are the antennas situated. Usually, this number is kept at half the wavelength because that gives us very good, well-behaved graphs. Now, this is not something that is hard and fast rule, in our derivation also, we could have put d as any value. We could have derived the antenna factor equation, and we could have plotted it very easily. But usually, say if I do say a very random value is 1.3 lambda, then we can see that we get three different lobes. This is just mathematics, by the way. This is how the array factor calculation will spit out its equation, and you can see that this is not super great for us because we were chasing directivity, and now we have three different directions from which radiation could be coming from, and we have no way of distinguishing between all of that. So that's why we don't use such values usually. And zero point 0.5 lambda is a sweet spot where we have good maths and good amount of directivity also, and we don't have such huge side lobes that are coming in. Yeah, so I'll stop sharing my screen.
You can continue with the presentation now.
Yep. I am trying to change the slide. Can you change the slide? Yeah. So one more thing that is a natural extension of these antenna arrays is a 2D antenna array. So all of this discussion was happening in just one dimension. These antennas were all lined up in just one straight single line. If I have an 2D array of antennas, say a square of antennas, all situated at certain particular distances, then that gives us beam steering in two different angular directions. So we can look at any part of our environment or any part of our sky with a very nice precision and nice directivity in some sense. And it's also a huge science of how these patterns can be created. Some people are experts in just how these patterns look. So in two dimensions, we can have an hexagonal pattern or a square pattern or a honeycomb pattern or any sort of other sort of these patterns, and we can have different sort of radiation patterns through it. So in the right hand side, you can see that there's a certain lobe that is moving around. This is again just how beam steering works. And if by changing the pattern of the antennas below it, the shape of this lobe can be deferred very easily. So in this way, we can use a multitude of simple antennas to create a complex design, complex radiation pattern, which can be used for looking into one part of our environment or one part of our night sky, for example, with very high accuracy, with very high directivity, yielding us a very good result. So usually you would see that instead of creating a very huge antenna, a lot of modern antenna systems are an array of antennas. They are all separated antennas which are spread out over a huge piece of land, and we can do interferometry or such antenna array techniques with them. One more extension to all of this is that instead of just playing around with the phases that from the electronically controlled phase delays, we can also add an attenuator there whose attenuation signal we know, and that in a sense helps us to reduce the side lobes even further and increase our directivity even more. So we can create more spindly shaped radiation patterns, and which can be useful to look into a more narrow part of the sky. And so that concludes our session. Throughout the session, we tried that your hunger for physics and knowledge in general is satiated by all of our talks. And finally, a very huge thanks to Horizon for letting us speak here. Huge props to Sri Kiran and Kirtana. They were the main workhorses for all of this. And thanks a lot for attending. Thanks so much.